Hi, my name is Ron Clark, and I'm representing Team 13, which includes myself, Ricardo Ontiveros, Brandon Benich, and Kaylin Conover. Our senior design project is the development of the electrical power system for SquidSat, a 3-unit or 3-payload CubeSat being built through the Sun Devil Satellite Laboratory and the Interplanetary Initiative, with launch planned right now for April of 2026. The challenge we set out to solve is how to design a reliable, robust, and modular EPS capable of handling power generation, storage, and regulation in the harsh conditions that are in space. Power systems are often one of the biggest constraints for the CubeSat missions, so the aim for our design is to overcome those limitations while creating a scalable architecture that can support not only SquidSat, but future ASU missions as well. At the start of the project, Team 13 focused heavily on the foundational engineering work through researching and comparing the components that would ultimately define the system's performance. Before any schematics or PCB layout could begin, the team conducted extensive comparisons of off-the-shelf regulators, chargers, protection ICs, and battery management solutions. This required evaluating efficiency curves, cold start behavior, thermal performances, and protection features, and flight heritage across a wide variety of devices. A significant challenge early on was the delay of receiving the finalized payload voltages and current requirements, which didn't arrive until late October. Because of this, the team had to consider a broad set of options, including the TPS 62130 family, the TPS 62903, and the TPS 63070, the LTC 3119, and several others. Narrowing these down to the most efficient and thermally stable devices would shape the rest of the EPS, determining inductor and capacitor size, thermal design, protection limits, and even what form factors were feasible for the final form.
Hello, this is Kalen Conover. The finished CubeSat electrical power system design consists of multiple important subsystems centered around the key components. This includes the battery charger IC, a Texas Instruments BQ25713, which has a built-in programmable maximum power point tracking system to manage efficiently charging the batteries in a 2-series configuration. So as regulators to provide power at multiple voltages to the various systems of the CubeSat, and a combined fuel gauge and protection IC, analog devices MAX 17320, that manages over and under voltages to the batteries. And there's also a redundant protection layer ensuring that there's hardware level cutoff in the event of a controller failure. Once components were selected, extensive simulation work was performed in LT-SPICE to validate the electrical behavior of the key components prior to hardware implementation. These simulations included the transient load response from the regulators to ensure that the output voltage stays within a 2% margin. Those thermal modeling, which showed that the battery charger IC remained below 60 degrees Celsius when outputting a constant 2 amps, and all the copper pores did not exceed 25 Celsius. It's also an efficiency simulation of the charging IC, which showed a 88% efficiency of power delivered to the onboard batteries. These checks ensured that our EPS design will be a reliable platform in performing its mission of providing power to a CubeSat, and will be able to do so over a long period of time without the risk of component failures. All the finalized schematics were created in blocks in Altium using custom libraries hosted in SDSL's Git repository. Symbol footprints were created or validated against manufacturer data sheets to ensure the footprint compliance prior to PCB layout.
Hello, this is Ricardo, and I'll be going over the hardware that Team 13 has created. So to start, I will say that this is Rev Zero, and we call it Rev Zero because it's going to be the starting point for the SquidSat EPS. One of our missions for this capsule was to create the foundation for a multi-generational CubeSat bus. That means that ASU will have its own hardware that we can reiterate upon, and ideally use it for as many missions as possible in order to make sure that our hardware isn't a point of failure for future missions. Regardless, every design has specific design requirements, which is why our designs are going to be kept in SDSL's workspace and will never be lost to time, as many previous designs have been lost. So with that, let me show you guys what we have created. So this is a PC-104 CubeSat form factor EPS. That means it's approximately 100 by 100 millimeters. This fits in the palm of your hand. It's a 4-layer PCB with a signal, ground, signal board stack up. Um, so after researching all of our components and deciding on which ones we wanted to keep, we've put all of the subsystems, as you can see here, into various schematic pages. For instance, I can show you one of our voltage regulators and our microcontroller schematic here. And all of those subsystems come together to create what we hope for is a robust 3U EPS, which has definite room for scalability. Um, we did opt to include a microcontroller into our EPS, which is one of the biggest changes that we decided to add. Upon doing so, the EPS can manage itself and run its own telemetry and communicate all of its findings to other payloads and the onboard computer within SquidSat using the CAN interface. So we were able to fit everything onto one side, apart from a couple of things on the back. Because this is Rev Zero and more of an experimental EPS, we only have 2 batteries in series. But now that we know that we have sufficient room, we can scale the battery pack up to make sure we have adequate power storage for the mission. So yeah, everything here comes together nicely. Here we have our remove before flights connectors and our inhibit switches will make sure that the satellite is stays off any power down state while it's in the deployer. Here we have our various voltage regulators up here. Our solar input comes in through here and then feeds into the solar harvester, as I call it, which is the maximum power point tracker from the solar array. This can be used with a 1 or 3U solar panels. And here we go into our battery charger IC and then into the batteries. So a lot of our design choices were based on heritage and what worked on previous missions and and good references that we found online. Once again, I probably said this many times, this is Rev Zero. The SquidSat team is going to take this design and expand upon it and make edits to make sure all of their mission design requirements are met.
And to wrap up our presentation on the SquidSat electrical power system, as we close, I want to step back and look at what this project represents. From the beginning, our goal wasn't just to design a power system that would work for one CubeSat mission. We wanted to build an architecture that could outlive this project, that could actually form something for future ASU CubeSat teams that they could adapt, adopt, and continue improving. The choices we made at every stage, our regulator selection, the monitoring structure, the modular rail design, were driven by the idea of longevity. We wanted to create a foundation that future missions can plug into without having to start from scratch. We wanted to create something that would help teams move faster, design something with more confidence, and build more capable spacecraft. Because of this EPS, we accomplished that mission. But just as important as the technical work was that happened through the semester, at the same time, a lot of things happened behind the scenes. Partway through the semester, we lost a teammate. It hit hard. It forced us to regroup quickly. Suddenly, each of us had more on our plate, more responsibilities, less room for error. Deadlines didn't slow down, and the mission didn't pause. So we had to step up our tasks, reassign things, cover missing roles, and support each other so nothing fell behind. And honestly, that experience shaped this project as much as the schematics did. It showed our ability to adapt, to carry the work forward, and keep pushing even when things got difficult. That teamwork and resilience are a big part of why this EPS exists in the form that you see today. So as we finish up, our hope is simple: that the SquidSat becomes more than just a single semester capstone. That this EPS architecture becomes a starting point for future missions, something reliable, flexible, ready for the next team to build upon. Thank you all for watching, and thank you for everyone that contributed to making this mission possible. We're excited to see how far future CubeSat teams can take this foundation. Thank you.